Okay, so for this example, you have a given fuel oil that is burned with 50% excess air. We want to determine the volume flow rate of the products with given pressure and temperature. So the fuel is burned at this mass flow rate, and then the fuel oil has the same characteristics as C12H26. So how do we do this now? No? So to find the volume flow rate, we need to find the mass flow rate. To find the relationship of the mass flow rate and volume flow rate, we need to find the density. To find the density, we need to find the molecular weight. To find the molecular weight, we would need the number of molecules, no? And then after that, uh, I think that's it. No, we also need to find the air fuel ratio. So let's get things started by doing the chemical balance first. So we have C12H26, and then plus you have, so since you have 50% excess air, so we can multiply the air, no? Basically the air is 1.5 times air, no? But there is also a coefficient here, an unknown coefficient of the number of air molecules needed. And then you have O2 plus 3.76 and 2, no? So this will be equal to, or sorry, react into, we have carbon dioxide, you have water or water vapor, you have excess air, so EaO2. So excess air is 0.5. I'll just write 0.5 here for the excess air. And you have N2, no? So Z N2. That's it, no? So we're assuming that this is a complete combustion since there are no other given, no? So to find this, we should start first with the C, no? So for the carbon, you have 12 carbon molecules is equal to 2x. So therefore the answer here is x is equal to 6, no? So for H here, so for H you have 26 on the left hand side, and then you have 2 hydrogen molecules times y, no? So 2y. So this will be again y is equal to 13. So divide this by 2 for both sides. For oxygen, we can equate this. So you have 1.5 times 2 of oxygen times A is equal to, so you have x here, no? So x is 6. So 6 times 2, okay, plus how many oxygen atoms here? So 1 only, no? So y is equal to 13, and then 1 oxygen here. And then how many here? No? So you have 0.5 plus 0.5 A multiplied by 2. So to find A, so we can find A here. I think I'll just use a calculator. No, maybe not. So I think I'll just write this off now. So 1.5 times 2 is 3. So 3A. And then 0.5 times 2 is 1. So we can transpose this to the other side. So this will be negative. So minus A is equal to, so you have 12 plus 13. No? So therefore, you can see here, A is equal to, or this will become 2A. No? So 12 plus 13 divided by 2 is 25 over 2. Or in other words, that is, um, huh? Am I correct? Just looking at my notes. Why is this different? Hmm, hmm. Where did I go wrong? So, if I'm correct, why is it 18.5? Hmm, divided by 2, divided by 2. Did I got something wrong? Is X this? Oh, I got the no the X wrong. Sorry. So this should be 12. No? So this should be 12 here. Oh, we got things wrong. So I look at this, no, the oxygen, it should be just X. My bad. Sorry, guys. So this should be 24. Or sorry, this should be 12. So this should be 24. Ayan. Good thing I looked at the notes. So this will be 24 plus 13 divided by 2. So you have 18.5. 18.5 as A. So the last one is Z. So to find N, the nitrogen, or for the nitrogen equation, you have 1.5 A. So A is 18.5 equals, sorry, times 3.76. Okay, is equal to 2N, no, or 2Z. So to find Z, just divide this. So 1.5 times 18.5 times 3.76, then divided by 2. So 52.17, right? Did I miss something again? Why is it different from this one? Oh, I forgot to multiply this by 2. Okay, so this should be times 2. Oh, times 2. So the answer should be 104, 104.34. Okay, so we got a working equation. So the complete one is you have C12 H26 and then plus, so I'll just simplify this, no? So 1.5 times 18.5, you have 27.75 O2 and then plus, so times 36 here, third sorry, not 36 but 3.76. So this will be 104.34, 104.34 and 2, and then equating this to, so X is 12, so 12 CO2 plus Y, so 13 H2O plus 18.5 times 0.5. I'll just simplify this, so 18.5 divided by 2 or times 0.5, it's the same thing. So 9.25 O2 plus Z, no? So 104.34 and 2. So we can find the air fuel ratio in the molal basis, no? So the air fuel ratio in the molal, no? Molal, that is molal, that will be equal to the number of molecules of oxygen, 27.75 plus, no, actually you can do this plus, um, 104.34. Okay. There is another way to do this actually. You can just, anyways, you can try, what you can try is you can do 1.5, sorry, or 27.575 times 4.76. That should have the same answer. Now let's check. So 27.75 plus 104.34. So this is the air fuel ratio on the molal basis. Or we can use also this 27.75 times 4.76. So that is the same thing, no? So you can do that as well. Okay, you can do that as well, no, an alternative. So this will be 132.09. So the unit should be kilomole of air, no, per what, no, kilomole, no, kilomole of fuel. So we only have one molecule, no? That is why we have one here. Just remember that. And you have the number of molecules on the of the air in the numerator. So to convert this to air fuel ratio, because we will utilize this later, no? We have a mass flow rate of the air here. We need to do the volume of the flue gas. So we can convert this into its per kilogram, no? Kilogram of air per kilogram of fuel. So we want to know the molecular weight, no? So the molecular weight of the fuel, we can calculate this. So 12, no? 12 times 12, no? Plus, so this is 12 times 12, and then 1 times 26. So this will be very big, no? So 144 plus 26, no? So 170. So 170 kilogram per kilomole. And then for the molecular weight of air that is given, also take note of this, 29, no, kilogram per kilomole. Or sometimes in other textbooks, this will be 28.9. No? You will only use 29 here. So to convert this, we can do some manipulation so that this 132.09 of kilomole of air per kilomole of fuel can be multiplied by this, no? So we have it should be up and down. So, hmm. So we should have, so this should be 29 per 170, no? So this is because we have kilogram of air here per kilomole of air, no? And this is kilogram of fuel per kilomole of fuel, no? So as you can see, we can cancel this out. What remains is kilogram of air per kilomole or kilogram of fuel. So the answer can be found, which you just multiply this 132. So we have a mass basis of the air fuel ratio, 29 over 170, and 22.533. So you have 22.533. So the air fuel ratio is 22.533. So kilogram of air per kilogram of fuel. So we can now find the mass flow rate of the air. So we can imagine, uh, so in a combustion chamber, we have here the mass of the fuel, mass of the air, and since we don't have anything else here, so everything should be converted into flue gas. So the mass of the fuel, mass of the air, and you have the mass of the flue gas. So we can say that the mass fuel, mass air is equal to mass of the flue gas. Diba? So we have given here is 45 kilograms per minute. No? Diba? For the fuel pala, no? But again, we can also find, hmm, we need to find the flue gas mass, no? We need to find the flue gas mass. Hmm. 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 Okay, so anyways, we can find the mass of air. We can actually find the mass of air using this 22.533 kilograms of air per kilogram of fuel by multiplying this by the mass of the fuel, which is 45, no? 45 kilogram of fuel per minute. So as you can see, we can cancel this out. We can cancel this one out. we have kilogram of air per minute. So we have this tool given, we can find the mass of the flue gas. So we have 22.533 no, times 45, and then plus the mass of the, sorry, it should be 45 here, sorry. And then we have 22.533, and then you have 45 to find the mass of the flue gas. So the mass of the flue gas is 533 times 45. Okay, 1058.985, no? So 1058.985, or I'll just write here 99, no? Anyways, I'll just write 985. No? So this is the mass of the flue gas. So to find the volume flow rate, this should be the mass of the flue gas divided by the density. Now, we don't know yet the density, but we can find the density. That is equal to P over RT. No? So the pressure and temperature are given. We don't have only the R, but is the molecular weight given? So it is not given, but we can find the molecular weight of the products, no? So this is the molecular weight of the products because we're talking about the mass flow rate of the products, or the fuel, no? That is wet, no? Or in other words, the flue gas. Yan. So we just want to count. Actually, there's a technique here, no? To do this. We can just utilize this everything here. A shortcut to finding the mass, the molecular weight when you have the chemical balance, no? So you have 12 CO2, diba? It's 12 CO2, and then 13 plus 13 H2O. Then you have 9.25 O2. Then you have 1O plus 104.34 of N2. So to find the molecular weight, it is actually simple to just do, no, to find the molecular weight, you can just find the sum of the number of molecules times the molecular weight of CO2. So let's say we have, so we want to find the sum of this over the total number of molecules. So let's start with this. We have 12 times CO2 is 44. Also 12 plus 32. Then you have plus 13 of the flue gas, no? That is wet. Huh. Anyways, 13, and then you have 18, and then plus 9.25. So oxygen is 32 plus 104.34, and then you have nitrogen as 28. Yeah. So what should be the one below? No? So this is the number of total molecules. No? So we just add 12 plus 13 plus 9.25 plus 104.34. So every coefficient should be added here on the denominator to find the molecular weight of the flue gas. So the molecular weight here should be, actually you can analyze this as well, no? So this is kilogram per kilomole of fuel. Okay. So this should be, let me calculate this. So you have 12 times 44 plus 13 times 18 plus 9.25 times 32 plus 104.34 times 28. Then divide this by 12, 13, 9.25, and 104. And so the answer should be 28.71. So 28.71, so kilogram of the flue gas, no, per kilo mole, of the flue gas. Okay, that is wet, no? So basically, to find the R, no? So to find the gas constant, we have to use the universal gas constant, 8.3143, no? Divided by 28.71. So this will be equal to So 8.3143 divided by ants. No? So 2896, 0.2896. So kilojoule per kilogram Kelvin. So the density can be found. You have the pressure. So the pressure is 102 APA. So that is atmospheric as well. 45, sorry, 350. So this will be 0.2896. And then don't forget to convert into Kelvin, no? 350 plus 273 Kelvin. So the density here can be found. So 102 divided by 0.2896 times 350 plus 273. And so 0.5653. 0.5653 kilogram per cubic meter. So you can analyze the units as well, no? But I won't do that anymore because I already know that this will be kilogram per cubic meter. But you can check, no? So the next thing we should do is we can input now the values here, no? So the volume therefore is equal to, so you have 1058.985, that is in kilogram of the flue gas per, actually just, I'll just write kilogram, no? So everything is the same here. Per hour ba to or per minute? It is in per minute, ha? So kilograms per minute. Then divide this by 0.5653 kilograms per cubic meter and find the volume flow rate. So you have 0.985, 0.56565. So 180 is 0.873, 0.32, no? 1873.32. Yeah, so this is in cubic meter per minute. Okay, so that's it. Thank you guys.